Hey, how's the sorting algorithm series going so far for you? Let me know in the comments. And welcome to episode 4. Today we're going to do Quicksort. So Quicksort is definitely on the faster end of runtimes for sorting algorithms. It runs in O of n log n time, and then it's faster than bubble sort, it's faster than selection sort, it's also faster than insertion sort. And then in Quicksort, what we're essentially trying to do is, for every number, we want to get all the numbers smaller than that number to the left of it, and then all the numbers greater than that number to the right of it. So at every instance, we're going to kind of like loop through the array and then get all the numbers smaller than that number to the left, and then all the numbers greater than that number to the right. So we're going to have a pointer that points to the current number that we're dealing with. I'm going to call it P. And then we're going to have a left pointer that's going to point to all the potential left numbers. And then we're going to have a right pointer that's going to point to all the potential right numbers. So let's do it. You initialize the left pointer one place to the right of P, and then the right pointer to the far end of the array. So when you're iterating through the array, there are three cases that we're going to look for. Cases where the left pointer is already less than the current number we're pointing to. In that case, it's in its rightful position, so we just skip over it. We increment the left pointer. And then cases where the right pointer is already greater than the number we're currently dealing with, the number we're pointing at. In that case, it's already in its rightful position, so we just skip it. We decrement the right pointer. And there are cases where both the left pointer and the right pointer are in their wrongful positions. They're not in their rightful positions. Like, say for example, the left pointer we should be less, it's greater than the current number we're pointing to, and the right pointer we should be greater is less. So we swap both the left pointer and right pointer. It's going to be easier as we go through the code. Let's just quickly go through an example. So we have these two pointers, right? These three pointers. We want to get all the numbers less than 5 to the left of 5, and then all the numbers greater than 5 to the right of 5. So iterate through the array. We get to 2. Is 2 less than 5? Well, yes it is. So we increment the left pointer here, and then we get to 4, right? Is 4 greater than 5? No, 4 is not greater than 5, so we do nothing. We leave it. We know that we're going to swap it at some point. And then we get to 3. Is 3 less than 5? Yes it is, so we increment the left pointer. And then we get to 1. Is 1 less than 5? Yes it is, so we also increment the left pointer, right? And now left pointer and right pointer are overlapping at 4, and then is 4 less than 5? Yes, 4 is less than 5, so we increment the left pointer. And now we're in an interesting case where we're at the end of the array, and then the left pointer is greater than the right pointer, so we stop. So at this point, we're going to swap whatever number our right pointer is pointing to, which is 4, with the current number that our pointer is pointing to, which is 5. So we swap them. 5. We've swapped them. So what have we done essentially? What we've done in this case is we've got all the numbers less than 5 to the left of 5, and then there are no numbers greater than 5, which, now that I think about it, this is a really, really bad example. And then all the numbers greater than 5 would be to the right of 5. But in this case, there are no numbers greater than 5, which is kind of like a bad example to choose. I'm going to choose another example, but let's finish this. So after that, we're going to go through another iteration, but now we're going to call the same quicksort algorithm on the left side of the array, and then on the right subarray, on the left subarray, and then on the right subarray. Just to kind of give you a hint that we're going to use recursion for this, and it works really, really well, because in cases where, say for example, the very first iteration divides the array exactly in half, we're going to do at most log of n calls to the recursive function, and we're going to have at most log of n calls in the call stack, at most log of n frames in the call stack, right? So that's it. Let me choose another example, maybe something like, let me think, 6, 8, 3, 2, 4, 9, something like that, something that maybe would have 6 in the middle. Okay, so we have something like this, 683249, and then we've initialized our pointer to point to 6, and then left pointer pointing to 8, right pointer pointing to the far right of the array. And then remember, we're going to have three cases, right? Cases where left pointer is already less than the number we want to swap, so we increment it, and then right pointer is already greater, so we decrement it. Cases where both left pointers and right pointers are in their not correct positions, I don't know how to say it, not in their rightful positions, and then we swap both left pointers and right pointers. Let's do it. So first of all, we look at the left pointer. Is 8 less than 6? No, it's not less than 6, so we do nothing, right? We move on to 9. Is 9? So the reason why we do nothing if 8 is less than 6 is because we might have to swap it in the future with another number. And then we look at the right pointer. Is it greater than 6? Yes, it is, so it deserves to be at the right. So we move a right pointer, decrement it, get to 4, and we say, is 4 greater than 6? No, 4 is not greater than 6, so it shouldn't be on the right. So, and then we look at the left pointer. Is 8 less than 6? No, it's not. So now we're in an interesting case where both the left pointer and the right pointer are not in their rightful positions, so we swap them. We swap left pointer with right pointer. We swap whatever number is at the left pointer with whatever number is at the right pointer. So let's do that. And that's it. So now our left pointer is pointing to a number less than 6, so we could safely increment it. And then our right pointer is pointing to a number greater than 6, so we could safely decrement it, pointing to 2 now. And then left pointer still pointing to a number less than 6, so we increment it. Right pointer is now pointing to a number that's less than 2, so we do nothing because we might have to swap it. And then we move right pointer one place, and now, boom, we're out of bounds, right? So we stop. And now we could swap whatever number our right pointer is pointing to with whatever number our actual pointer, this guy right here, is pointing to. So we swap 6 and 2. And we're done with that. So what have we done here? Well, remember we were looking at 6, right? Remember we were looking at 6, right? We've essentially put all the numbers less than 6 to the left of 6, and then all the numbers greater than 6 to the right of 6. And now we can call the recursive function on the left subarray and then on the right subarray. So if we call the recursive function on the left subarray, you kind of get the idea. I'm not going to go through the entire example because of time. I want to make this video really, really short and entertaining. So if we go through the left subarray, we're going to have 2, 3, 4, 6, 8, 9, something like that, right? But there is a technique to the order in which we call the recursive function on both the left subarray and then the right subarray. So we call the recursive function. You can do this in any order, right? But in terms of optimization for space, we're going to do a slight optimization for space in terms of the order in which we call the recursive function. So you first call the recursive function on the smaller subarray before calling it on the bigger subarray. Because if you call it on the bigger subarray, what's going to happen is you're going to risk having O of n calls on the call stack because of recursion. Recursion stores frames on the call stack. But if you call it first on the smaller subarray, you're going to have at most log of n calls on the call stack, right? So what do I mean by that? So for space complexity, say for example, we've divided the array into the very first iteration, divided the array into 2 subarrays. Let's say this is one subarray. It's 1. One subarray has a value of 1, and then another subarray has 4 values in there. So if you call the recursive function on the bigger subarray, what you're going to do is we're going to have 4 frames on the call stack before calling it on this single guy right here, before calling it on the 5th frame. So first of all, you have to take care of this frame, this frame, this frame, and this frame before taking care of this final frame. So you're going to have like 5 frames on the call stack. Actually, at most, you're going to have 5 minus 1 frames on the call stack. That's 4 frames, which is kind of like O of n frames on the call stack, right? But what if you call the recursive function on the smallest subarray first, let's say of value 1, just one value, it's going to take care of that first before going to the other subarray. So what's going to happen in this case is that tail recursion is going to take its toll on this particular situation. So if you don't know what tail recursion is, in simple terms, it's like if the recursive call is the very last thing you do in the function, and then it's kind of like an O of 1 operation. I really advise you to look it up. It has a amazing academic explanation and illustration. Look it up on Wikipedia, and then you learn more about it. So in this case, we call the recursive function on the smallest subarray, which gets taken care of. So that's an O of 1 operation because of tail recursion. Look it up. And then you have this subarray. And then because of the way we're implementing Quicksort, we're going to divide the subarray into two halves and then call the recursive function in this half and then call the recursive function in this half next. So when we divide an array into two equal halves and then call recursive function in them, it's going to be a log of n runtime. So for space complexity, we're going to have at most log of n calls on the call stack. There are people who do like really cool visualizations of this, and it would be cool if you could check it out, but that's way beyond the scope of this video and way probably beyond the scope of your interview. But if you can explain why you're going to have at most O of log of n calls on the call stack, that will be a plus for you in your interview. So I feel like I've ranted a lot about Quicksort because I really like the sorting algorithm, but let's dive into the code for it. Alright, so I took up some of the code for selection sort. That's where we left off with episode 3, but I left the swap function because we're gonna reuse it. So first of all, what we want to do is we want to write a helper function to do Quicksort. That's the recursive function. I'm just gonna call it public void apply Quicksort, and then it's gonna take in an array. It's gonna call it integer array. It's going to take in a left pointer and then it's going to take in a right pointer. Instead of saying left and right, let's just say start, right, and then end. And then after this, we can just apply Quicksort on the nums array, and then we're going to start at 0 and at nums.length -1. So first of all, let's take care of a base case. So if start is ever greater than or equal to end, and then we can just return, right? And now remember, we have to take care of three cases where both the left pointer and right pointer are not in their rightful positions. We have to swap them. So if the left pointer, if the number at the left pointer, let's say if array at left, I just realized we don't have a left and a right, so let's do that. So int left is equal to start +1, and then int right is equal to end. If the number at the left pointer is ever greater than number at start, instead of, let's just have a pointer, let's just say int pointer is equal to start, let's just say pointer, and whatever we have at the right is less than array at pointer. So if this is ever the case, it means that both the left pointer and right pointers are out of place, so we should swap them. So call the swap function on the left, array left and right, and that's it. Our second case is if the left pointer is already less than or equal to, if array left is already less than or equal to whatever our pointer is pointing to. In this case, we increment the left pointer, so we do left ++. And then we take care of our third case if whatever the right pointer is pointing to is already greater than or equal to array at pointer, In this case, we decrement right. I think these are the only three cases that we definitely need to take care of. And then at the end of this while loop, oh, I realized we don't have a while loop. We need a while loop. So while left is less than right. It's like I know how to solve those things in my head and I just breeze through them. So after this while loop, our rightmost pointer is going to be pointing to the number that we want to swap with whatever our current pointer is pointing to. So we swap and the array right and pointer. And now we have to apply the quicksort algorithm on the left subarray and then on the right subarray. But remember I said something about the order in which we apply the quicksort algorithm because of a slight optimization that we could do with space. So first of all, we want to apply quicksort on the smaller subarray before applying it on the larger subarray. So we have to determine which subarray is smaller. So let's say left is smaller is equal to, so where does the left subarray start and where does it end? So it ends at right -1 and then it starts at start, right? If this is smaller than the right subarray, so where does the right subarray start? It starts at right +1 and then it ends at end. So end minus right +1. So if left is smaller, we want to apply quicksort on the left subarray first. Otherwise, we apply quicksort on the right subarray first. So we call the quicksort function, apply quicksort, and then array. This time we're going to start at start, I think, and then end at right -1. So this is just calling the quicksort algorithm, the recursive function, on the left subarray, and then let's do it on the right subarray. And then for this, we're going to start at right +1, and then end at end. And then otherwise, we do the same thing, just that in reverse order. So first apply it on the right subarray, and then apply on the left subarray. And that should be pretty much everything we have to do for quicksort. Just quickly going to make sure that we have everything. And let's run this. Interesting. Oh wait, I think we have to put an equal to sign here, because then we're not dealing with this final case. Or for our output, I think we got 2 correct and then we got 1 wrong, so that we were off by 1. Awesome. So that was the problem. So this is off by 1 errors. They're really, really easy to fix. Just look for cases where you have to put an equal to or less than or something like that. So let's submit this. This is our fastest sorting algorithm so far. Awesome. So you can see that it's really, really on the faster end of runtimes. It's in the 78th percentile, which is really good. So let's dive into the time and space complexity of quicksort. So for time complexity, the best case time complexity is going to be O of n log n. So that's O of n log of n. Because in the best case, let's say we went through the array in one pass, that's in O of n time, and then we divide the array into 2 equal halves, and then we call the recursive function on 1/2, that's a log of n times, so that's n times log of n, so that translates to O of n log n. And then for the average case, it's going to be the same thing, O of n log of n. And then for the worst case time complexity, this is going to be a tiny bit trickier. This is going to be O of n squared time. Why is it O of n squared time? Remember, we had a really, really terrible example, the very first example that we did. Let me go back to it. It's this guy right here. So 5 was here in the beginning, and then when we went through the first pass, that's O of n, we ended up having 5 over here at the tail end of the array. So we had to make the recursive call on this subarray, and this subarray is O of n minus 1 length, because removing the 5, which is O of n, kind of. So it's like O of n times O of n minus 1, so it translates to O of n squared time. So in the worst case, it's like you have a very big number at the start of the array, and then you iterate through the whole array, and then you ended up having the big number at the end of the array, and then you have one subarray that's really, really huge, and then the other subarray is very negligible. So that's an O of n squared time. So that's it. For space complexity, we're doing O of log of n because of the tiny bit of optimization that we did, calling the recursive call first on the smaller subarray before calling it on the larger subarray. So that's it for Quicksort. It's a really, really fast algorithm. And then if you like this type of content, please consider subscribing to the channel. Comment down below. Let me know if there are other innovative ways we could implement Quicksort. And then like the video for the YouTube algorithm. I'm really trying so hard to finish the sorting algorithm series. And then we're going to go through something I'm going to call an easy streak on LeetCode. So we're going to solve a bunch of easy questions on LeetCode. So stay tuned for that. And then share it around the community. And I'll see you in the next one. Bye-bye.